right, so let's start with the final lecture for today, which is on conditional valued risk. But before that, let's look into some critiques of valued risk, which I just explained in the lecture before. Well, the reason why I focused at the valued risk first is essentially twofold. One is that you need to understand valued risk before we can move to the conditional valued risk. But the other reason actually is that valued risk is a widely used model in the real world. I mean, in the banks and in the pension funds and so on. Valued risk is actually a measure, a risk measure, which is required by law to report to financial supervisory authorities of several countries. Essentially, all the banking kind of regimes under the so-called Basel Accords, Basel II Accords, they are required by law to report their valued risk numbers to the authorities. And it's normally on either on a daily basis or weekly basis or monthly basis, depending on different circumstances and different portfolios, right? But we just went through what valued risk was. Let's look into what is the problem with valued risk. Well, there are a number of problems with valued risk, and the first of which I'm going to focus at is that valued risk is not a so-called coherent risk measure. And what is a coherent risk measure? There's a paper by Artsner et al., which I have actually referenced to you in your lecture notes. You can have a look into this paper later if you like, where they define what they consider to be a coherent risk measure. And by coherent, they mean a meaningful, a risk measure which actually makes sense, right? So it's something that has got some desirable properties. And those desirable properties actually, they summarize mathematically as these four ones. So you say any risk measure has got some, should have some desirable mathematical properties, which are monotonicity, sub-additivity, positive homogeneity, and translation invariance. And they discuss in depth how each of these properties translate into some requirements which are reasonable to have in regards to risk measures, right? And then they use that to say, well, some of the more popular risk measures are actually not coherent in that sense, in their sense of what is a kind of sensible risk measure. They first argue what sensible risk measures are and why these properties are sensible. And then they say, well, if you then do not abide by any of these requirements, then you are not a sensible risk measure, right? And they in particular look into two risk measures that they criticize. One is actually valued risk, that they simply state that, well, that one violates the second property. And I'm going to get into that, what that actually means. They also look into portfolio variance, the Markovitch risk measure, right? And they say, well, that's not a sensible risk measure either. So far, you have been introduced to portfolio variance and also portfolio valued risk. And then I'm saying, well, both of these risk measures are actually not sensible, at least from Artsner and his colleagues' point of view. And as far as these four mathematical properties are concerned. Now, let's argue why valued risk, in their view, is not sensible. So they say that valued risk violates the second property of these coherency properties, these four properties for a sensible risk measure. The second one says sub-additivity. So that means that valued risk is not sub-additive. What does it mean? So let's say I have two portfolios. I have portfolio 1 and I have portfolio 2. And these portfolios, they've got a risk here. And this one has got a risk here, right? So these are the two portfolios that I have got. And let's say that the guy in charge of portfolio 1 and the guy in charge of portfolio 2, they don't talk to each other. They are maybe part of the same organization, part of the same enterprise, but they don't talk to each other. It could be practical reasons, but it could be also that they are, even by law, they're not allowed to talk to each other. There has to be some kind of Chinese walls in between them in terms of regulations and what have you, that this one maybe is the internal portfolio of the bank. This would be something sensitive to the clients. You don't want to bet against your own clients, so you don't want these two portfolio managers to talk with each other, right? So those situations easily occur in bigger banks. And in many cases, you might not only have two portfolios, but you might have several, tens of portfolios or hundreds of portfolios in your total organization. Now, what is the idea of with sub-additivity? So what we want to do is that I want to find out what is the value at risk of portfolio 1. So I'm the manager of portfolio 1. I can measure that, right? So I can measure my value at risk for portfolio 1. And the guy who's in charge of portfolio 2 would then measure the value at risk of portfolio 2, right? But we don't have the sum of these two portfolios. So it would be nice, wouldn't it be nice, that if I say value at risk of portfolio 1 plus value at risk of portfolio 2, that has to be greater or equal, so it's kind of an upper bound, right, to value at risk of portfolio 1 plus 2. Because at the end of the day, if I had this bank with these two portfolios, what I'm concerned with is the sum of portfolio 1 and 2, not the ones individually. But for practical reasons, I only have the measures for number 1 and number 2. So this is what is called in mathematical terms sub-additivity. Sub-additivity means some function of x plus the same function of y is greater or equal the same function of x plus y. This is essentially what sub-additivity says, right? So you have it probably from some calculus course, some analysis course earlier in your engineering studies. You probably heard about all the other ones, and you happily forgot all about that, but you can go and reread it, look it up on Wikipedia or on your old books, or look into the paper of Artsner et al. Right, but this is sub-additivity, and what they say is that this is actually not true when it comes to value at risk. So you can construct portfolios that essentially is the opposite, that when I put portfolio 1 and 2 together, then the value at risk of the total portfolio is actually higher than the sum of the individual portfolios, the value risk of the individual portfolios, which is not a desirable kind of property, right? Because if I were in charge of the total risk management for this bank, then I can't do that. Then I don't have that upper bound. And the reason for that is that essentially, there is this effect that you're cutting this tail, and you're here cutting this tail. But if you put the two together, then you might be including some of the values in the tails all of a sudden in this portfolio over here. So the more you put your portfolios together, the better your value at risk actually becomes, which is not really a nice property, right? You can also think of it a different way, is that, well, value at risk essentially is just cutting the tails and throwing it off, right? And so all of a sudden the tail doesn't matter anymore. So those extreme values kind of we lose them, they get lost, and as a result of that, this property is not true either. So that's kind of the intuition behind that. Right, so that's one problem. And then they say, well, if we look at CVAR plus CVAR of portfolio 2, so that was the average of the losses in the tail and the average of losses in this tail, then it's true, then it's less than the CVAR of portfolio 1 plus portfolio 2. Right, so this one is true. And for VAR, it's not true. So that's also the reason why back in, I think it was 98 or 99 when they wrote the paper, that was around the same time where people in Basel in Switzerland, they were working on the Basel Accords. And they had actually gone quite far with looking into value at risk. There was a book by Jurian written back, I think, in somewhere in the 90s about value at risk and explaining that it's actually, it has some, value at risk has got some appealing properties, but it was from a mathematical point of view maybe not completely thought true, right? So the suggestion of Artsner and his colleagues was that why not change from value at risk and actually make CVAR into something that you want to ask banks to report. But by the time they got there, I think it was too late, so they didn't really get through their message through the Basel. And as we have it still today, value at risk is the measure that you have to report to financial supervisory authority. So many times, even though you have a better alternative, but for practical reasons, you can't really get your message through. It's got to do probably more with politics than with math or finance, for that matter. Right? So, but this is, as far as the finance of it is concerned, conditional value at risk is definitely a more coherent risk measure than value at risk. This is one of the reasons. This is sub-additivity. The other one is just essentially pure kind of common sense, right? So this is the example from that very book, Jorian, the book on value at risk, which shows the distribution of returns of the LTCM. Maybe somebody wants to do a presentation on LTCM. Anybody has heard about them? Long-term capital management. There were, I think there were 4 guys, maybe 3 of them had a Nobel Prize in finance. They got together somewhere in the 90s and they started long-term capital management. And they were doing quite well for a few years, making kind of extraordinary returns, until at some point, I think that was in which year was that? I think that was somewhere in the 90s, probably around the same time, I guess. I think probably that was in the 96, around the Russian bond crisis. Was it 96 or 98? I don't know, maybe it's just a more recent version of the book. But anyway, that within a couple of months, they had, these are monthly returns of LTCM. They had a single month where their portfolio lost, I think this is 90% or something like that. So 90% of its value was lost, and they got billions of assets under management, billions and billions of, maybe, well, billions not really much in that, probably that was hundreds of billions or thousands of billions of dollars assets under management, and they lost 90% of that. So that was the impact of that was huge. And you can read about that. There are a couple of videos on YouTube which explain exactly, you know, what happened, who was behind LTCM, and what exactly happened. But there were a few months that they had some of these big losses, but there are only a few months. So this is their returns. You know, that there were many months that they were making, you know, they were having positive returns. Actually, the majority of the months, these are, you know, the majority of the probabilities are on the positive. Monthly returns of, you know, 3, 4, 5%, these are quite impressive, right? But there were also individual months where they almost lost everything. And at the end of the day, they went bankrupt, right? So within a few months that happened. And essentially, if you were looking at their value at risk, and this is, I think this is I don't know if it's a 1% or 5%, but it doesn't matter. If you're looking at some value at risk, essentially what you're doing, you're cutting off the most important information away. So why is it that you want to go through this extreme efforts into finding out, you know, if you have, even in this case, historical scenarios that this particular portfolio has lost, this fund has lost a huge amount of money, that you want to actually go and figure that out, find out, well, this by no way, this looks like a normal distribution of any kind. And what is interesting about this is exactly this is the tail, right? But why do you want to cut it and throw it away? So that's the idea, that's exactly what value at risk is doing, right? So back to the idea that it's a quantile. What we are interested in is to look at these guys and say, well, the true risk of tail of this portfolio is, let's say, the average of these guys, or is even their worst case, if you like. But at least take them into consideration in one way or the other. So that's the second reason why we prefer conditional value at risk to value at risk. Well, and finally, let's get into how is it we model that, right? So again, note here, we had the standard deviation. This is just showing how much you deviate to the left and right of the average, right? So this is not really standard deviation from this picture already. If this was distribution of losses, that already gives you also an idea why a standard deviation is not a good risk measure. That's another reason why it's not, because who really cares about the deviations around the average if your true distribution has a long tail, right? Your true risk is in the tail, not in how much you deviate from an average. If you had a normal distribution of returns, then portfolio variance is a reasonable risk measure. But if you are dealing with distributions like this, then you have to care about the tail, not so much about deviations from an average, right? And Well, value at risk kind of comes close to that, but then it just cuts off the tail. Conditional value at risk gets the average of the tail and looks into that. So that's why we look into conditional value at risk. And let's see how we actually model that. So this is the conditional value at risk model. This looks very similar to your value at risk model. In fact, there are only a couple of equations which are different. Well, for one thing, we are minimizing then conditional value at risk, which is a variable. It's a free variable. So we are minimizing conditional value at risk. And notice here that 1, 2, 3, 4, there are 4 equations which are completely identical with the model from before. So I'll go quickly through those. Again, we want to make sure that we buy the portfolio based on what is our budget. So we want to buy for the whole thing. X is positive weights on the portfolio we choose. Then we're saying the average return of the portfolio has to be greater than some given average return target. Here we calculate the losses again. So loss is how much we are below the budget we came up with in this case. Loss is just the opposite, the negative of returns. And then you have value at risk deviation. Again, we want to find out if the scenarios for which the losses are in excess of value at risk, we save them in this positive decision variable called VAR-DEV. So far, it's just a repetition of what we went through for the VAR model. But now comes the new. So there's one equation which replaces the last 2 equations of the value at risk model. And notice, in some miraculous way, the Z is gone. So there is no binary variable here. So here comes essentially the third, from a mathematical programming point of view, the third advantage of the value at risk. It's actually an LP. It's a linear program. It's not an MIP. So it's actually, well, it's a nicer model. It's actually easier to solve as well. So what's not to like? All right, so that's the thing. And you can think of it, I tend to think of this, I mean, the more kind of elegant mathematics normally you get, it's also, you get easier solutions to that. So normally when you get into binary, the 0, 1 variables, they come in quite handy for some practical problems many times where we have to do with kind of where you have had some lawyers or some politics of some sort, or some legal issues. If you want to model those things from a mathematical point of view, those are kind of ugly constraints. Normally they will kind of force you into some 0, 1 variables. Whereas if you are looking into normally kind of things which are more like laws of nature or things of that sort, then you don't really need the 0, 1 variables. This is, well, maybe a bit of an exaggeration, but in this case, that's definitely true, that you are looking into a model which is mathematically more coherent, and at the same time, also from an optimization point of view, it's more elegant to solve, if you like, right? So here is how we measure the conditional value at risk. We say conditional value at risk is then value at risk plus what comes on top of the value at risk, which is a deviation, which we just measured here. So that's the deviation on top of value at risk. So we sum that up for those probabilities, and then we weigh it with the probabilities for those scenarios where the loss is in excess of value at risk, and then we normalize it with the probability that we have. So if we had the 95% probability, this thing then is divided by 0.05, right? By 5%, right? In order to have the same level, in order to make sure, because value at risk is exactly, so let's say if my value at risk was, in this case, there's a 5% loss, right? And let's say just say if I had 5 cases here, so in 5 cases I get 6, 7, 8, 9, and 10, right? So what happens then? What is the average of those guys? This is this is this is 6, 7, 8, and then the values I have for those on the value at risk on my VAR-DEV, that would be 1, 2, 3, 4, 5, right? And the average of those guys is 3 that I want to put on top of 5, so I want to get to 8, right? So my C bar then is 8, and I want that value to be 3. But what happens then in that sum? So let's say I have the probability of 100, right? So I have, then I say, well, that's 1 plus 2 plus 3 plus 4 plus 5, right? And this whole thing divided by 100, right? What does this give me? So 3, 6, 10, 15. So that's 1500, right? And then I want to divide this thing. So this is 1500. And I want to divide this by 0.05. If it's a 5%. So that would be exactly 3, right? So this is essentially about getting, because I'm dividing by the minus 100 here, but only I have 5 scenarios, so this corresponds to 5% of the total mass. That's why I divide by that to get back to an average that is normalized compared to the level I'm working with here. So that's essentially the idea of that normalization. Yeah.
You sum up P and bar F, or you just sum up P and then multiply with bar?
Well, I mean, it goes to the same thing, right? I can just put if you have, if I had 100 times 1 plus 100, so you can just take it out, right? So it's the same thing. Yeah. So this is the definition of conditional value at risk, and the last slide for this lecture. Any questions? I'm sure you will have some when you start working with it later. All right, thanks. Let's take now the longer break until 3 o'clock, and then we go to the exercises.